Welcome back from lunch. Thanks, everyone. Hi. Hi, my name is Adam Crafts, and today I'll be presenting Where Are We with AutoML. All right. Hopefully the chatters for excitement of this talk. So let's talk about the progress in AI. So in terms of what has happened from AI over the years, in the beginning, things that were called artificial and intelligent weren't really learning anything. There were a lot of handcrafted predictions. A lot of the systems were rule-based, not necessarily learned. And then eventually people started using machine learning for learning the predictions. However, a lot of the features inputs that were input into the machine learning models were still handcrafted, and a lot of tricks people were using. Now we're currently getting to what we know as deep learning, where we're learning the features and the predictions end to end, which is great. So a lot of people would say, yeah, maybe we're done with ML, it's data in, data out. But that's really not the case because there's still a lot of handcraftedness going on. There's still a lot of people designing different architectures, different ways to pre-process the data, the algorithms, the optimizers, all these things are still somewhat handcrafted, right? So then going forward, how can we learn to learn? How can we really have automated ML where the algorithm, the features, and the predictions are all learned and optimized in an end-to-end manner? And really, we kind of drive down the handcrafted work that we're doing. So why is this important? So a lot of you in this room probably have worked with machine learning, which is great. You may work at organizations that have lots of data. So hopefully I don't have to explain to this crowd that there are a lot of organizations that have data and have uses for machine learning. Some of them are very practical and obvious. However, there's still millions, there's other organizations that don't even know that they have machine learning, or that they know they have data, but they don't really understand what machine learning is, or they don't know how they can start working with machine learning. And then on the other side, on the practitioner side, there's only tens or maybe hundreds of thousands of people that are trained to actually solve these machine learning problems. And this is going to continue to grow. There's going to be organizations that have data and problems that can be used with machine learning. And it's great that we're training more people to use machine learning, but it might be tricky to keep up with the demand. So the question is, how can we meet the future demand of ML expertise that is needed to solve these problems, as well as the people that are currently working on machine learning? Can AutoML be used to enhance their workflow, to make their problems better as well, so that they can focus their time and energy on more important tasks in the machine learning process? So hopefully it makes sense that looking forward, things like driving down the cost and availability of machine learning is important. So the question is AutoML something that we're just striving for? Or is it actually something that can work and make an impact? So the answer is yes, that it is feasible. And this has been shown over the past few years. So in different domains and modalities, AutoML has already made huge strides in machine learning. If you look at this chart, which some of you may be somewhat familiar with, where you have the ImageNet accuracy results over many, many years, a lot of these networks were handcrafted, hand-designed by humans who came up with different tricks to continue pushing the envelope, getting better results. And then in 2017, we started coming out with AutoML methods that not only matched the machine learning experts, but actually outperformed them. And so this was a pretty big breakthrough in the sense of answering the question, is it feasible? The answer is yes, and in many cases, you can get better results than human machine learning experts. And this trend over the years is going to continue to grow in terms of using AutoML. So the question is, where can we use AutoML? Is it just on ImageNet recognition challenges? Is it just on designing the neural network architecture? Let's find out. Here's a very simple view of a machine learning development pipeline. So you might have something to the effect of you have your data preprocessing input. How do you feed your data into your model? How do you transform it? How do you augment it? Things like that. You have the modeling aspect, which nowadays, if you're using deep learning, is really about neural networks. How do you pick a good model that's going to work for your task, or how do you design one? And then on top of this, there's the optimization piece, the actual algorithm that says, given this modeling and this data, how do I learn the best parameters and set of weights that will actually achieve the machine learning task? And the answer to where can AutoML be used is really everywhere. So here today I'll show you some examples, but you can really think of AutoML as not just being targeted towards one specific part of the machine learning process, but you can really look at it at solving different components. And I'll give a few examples. So for the data input piece, if you think about the data sets that you have, oftentimes people will augment the data such that their data set artificially looks larger. And so what do you do in that case? Maybe you've looked at another paper or example code or something that you've tried in the past where people have done some augmentations, some different transformations that make sense. Or maybe you just try out some on your own and you get better results with different things that you try. However, why not do that in a more data-driven approach? So this paper, AutoAugment from 2019, basically showed that you can actually optimize the process of learning the augmentation itself. And in this case, AutoAugment actually showed to make huge gains by doing it in a more data-driven approach. What about other parts of your data input pipeline? So we all know about machine learning and the need for labeled data. So that would be supervised machine learning. But what about semi-supervised machine learning? So that's the concept of you have labeled data, but then you also have volumes of unlabeled data. And in practice, in industry, this is actually pretty common, right? Because you'll have some pipeline to have people check or label the data, but oftentimes your systems are still getting more data in real time that's not being labeled as quickly. So it's pretty common scenario where people have a set of labeled data, which could be big, could be small, but also an even larger set of data that's not yet labeled. And so how can you use that? So this is one example. This is a recent work called Self-Training with Noisy Student. And what happened here is the process is that you first learn a model on the labeled data that you have. And then you call that the teacher model. And then you run the model on all of the unlabeled data. And on all of the unlabeled data, you create what are called pseudo-labels. So it's not just one class, but you actually have this distribution over the possibilities of different classes. And you could stop there. Sorry, you can't stop there yet. So then you have this teacher model that's essentially added pseudo-labels to this unlabeled data. And then you train a student model that the goal is to predict the original labels on the labeled data set, as well as the pseudo-labels that were pseudo-labeled by the teacher. And then there's some other techniques where you add noise to the system in the form of data augmentation, dropout, and stochastic depth. And what ends up happening is that this teacher, the student model can actually learn better than the original teacher on just the labeled data. And so that's great, you can stop there, but actually you can keep doing this. So iterating back and forth where first you have a teacher that trains a student, and then that student becomes the teacher, and then you train another student. And in this iterative manner, you can actually get really good results. So this is one other way where AutoML can be used to improve the data input of your system. So moving on to modeling. For modeling, one interesting aspect is, have you ever thought about the actual functions and operations that you're using in a neural network? Oftentimes those are really like what's available in the code that you're using. Well, AutoML can actually be used to learn new operations. So in this example, AutoML was used to search for new activation functions, and it learned that this function, f of x equals x times sigmoid of x, which is now called swish, can actually make improvements for many people's cases. And so here, the image is showing the blue line is a very common activation function, ReLU, and the red line is what was learned. This is the function. So you can think about using AutoML to actually design different parts, different operations of the modeling part itself. And then another aspect of modeling is what's called neural architecture search. And this is really a really important and big field in the concept of AutoML. So this is from the first paper in 2017, where instead of designing the network by hand and trying different parameters, there was a machine learning piece that actually learned different blocks within the network and how to connect them. And you get this really interesting picture of connections that it would be hard to argue that a human would purposefully design that. So some things to highlight here is that this is sort of the beginning in 2017, but this has really exploded into a pretty broad research field in many areas in terms of designing different ways to search for more interesting architectures. I'll talk later about how to make these methods more robust, drive down cost. But this can be a really important piece of AutoML. So moving on in the optimization, so oftentimes, again, you'll take something that's off the shelf, or something like an optimizer like Atom or RMS Prop, which has these fixed update steps that that a human decided these are the steps that have some different properties. But even in this case, AutoML can be used to create new and interesting update rules that can, in some cases, actually outperform the traditional optimizers. So hopefully that gave you a sense of the fact that AutoML is not just one aspect that's targeting one piece of your machine learning pipeline, but can actually be applied to many different areas. So that's great. Let's talk about what it is. How does it actually work? All right, so in a nutshell, AutoML is essentially taking your existing machine learning program and task and wrapping it in an outer loop. And we'll get more into what this means. But you can think of, if you have a program where you're already training something, that's what's shown here in the inner loop, where you have a task and you're training it and trying to get good results. And so now we have these different components, this controller, these parameter choices, and the feedback. And let's talk about the different components. So the controller is itself an acting entity, and its goal is to tell the inner loop a set of parameter choices that the inner loop should try to give the best results. And then the inner loop, after it's done, is going to output some feedback or reward back to the controller. This slide here is showing that the controller could be something very simple, like grid search or random search. So in that sense, it really wouldn't be learned. So grid search or random search would be just taking all the parameters or different things that you want to sweep over and try every single permutation. Or random search is literally just trying out a bunch of different random things. But in that sense, the feedback really isn't going to change how the controller outputs things. However, you can also use smarter methods that are actually learning something, such as reinforcement learning, where you have this agent that's trying to output the parameter choices given the feedback. It could be evolutionary based, or it could be a gradient based method where you're actually trying to optimize some set of weights in the controller itself. And so the takeaway here is that if you have been exposed to some form of AutoML, you might have seen that this particular method is using this particular type of controller. However, there are different types of controllers, and even within these, there are different ways to, there's not really one type of way to do reinforcement learning or evolution. So there's a lot of work just on the controller aspect of AutoML. So what is the controller output? Here I've called them parameter choices, but you can think of them as either like knobs that the inner loop has exposed that can be tweaked. But examples of these would be things like if you're designing a neural architecture, the number of convolution filters, maybe the number of layers. It could be, like I mentioned earlier, different augmentation operations. And the goal of the controller is to, over time, learn how to output better parameter choices. So maybe it starts out kind of random, but then over time, the goal is to have it tell the inner loop basically, oh, I think these are the best set of parameters. And that's really the output of AutoML. And so the controller needs to, in many cases, learn. And to do so, it needs to get some feedback of, oh, I output these parameter choices. And based on that, here's the certain feedback or the reward that I got. So a simple reward would be if you have an inner task that's training some, let's say, classification method, it could be the accuracy or the loss, which then you're trying to either maximize or minimize. But here I also mentioned that you can also add additional penalties. Like the feedback doesn't need to be just the metric itself, but you can add different constraints, things like memory and runtime. And this is actually a really key point, because without constraints, your controller may just learn to output the larger options, whether that's larger filter sizes, larger numbers of layers, because those tend to get better results. So this is an image from a paper called MNASNet, where the goal was to search for architectures on mobile devices. And so this diagram from the paper itself looks similar to the diagram I just showed you, where the controller is outputting different parameters for the search space, and then the trainer, which is the inner loop, collects some accuracy. But at the same time, what happens in this system is that you actually take the model that was trained and you run it on the mobile device, and you collect latency. And then the feedback that you actually give to the controller is a combination of the accuracy with a penalty for latency. So this, again, like I said, is a very key point, because oftentimes if you're using a network that someone else has trained, it may not be the right choice for your system. Especially, consider if you train on GPUs or TPUs, but then you're actually running on an embedded device, or maybe you have some company with proprietary devices that it's really not the case that the operations that were good on a GPU are going to be necessarily the best for your actual platform. So not only is this good to kind of give you better results, but also can give you sort of personalized results for AutoML. And, so the takeaway here is that for your specific hardware system, you can really think about adding constraints to the AutoML, which really can sort of tune and target your particular hardware or system. Okay. So what about cost? If you think about right now, the machine learning can be pretty expensive to run, even for the concept of this inner loop. And now we're wrapping this in an outer loop, and we're asking this feedback to happen. So doesn't that just drive up the cost and like multiplicative factor? So the answer is the first approaches that we're using AutoML, the answer is yes, it was fairly expensive, but really the goal at that point in time was to show the feasibility in terms of, is it possible for AutoML to actually match or exceed human experts? So now there's a lot of focus on how can we drive down the cost. So if you think of this big sort of double for loop where you have this inner task and then this outer loop, one thing you can do is sort of shrink or decrease the cost of that inner loop. So for instance, instead of having the inner loop train your entire data set to completion, you can use what's called a proxy task. So this can be a subset of your data, a different data set, smaller parameters to some degree, but the goal is that it resembles your actual task that you want to optimize in the end. And so the goal there is that if you have lower inner loop costs, maybe you can try out more things and then hopefully come up with a better solution. Another idea is called early stopping. So maybe the controller outputs some parameters, you start training, and you notice pretty early like, oh, this experiment's not going very well. So you can actually take that experiment, exit it early, and therefore not all of your inner loop experiments are going to be the same cost. And that hopefully you're, again, saving on the compute itself. So these methods do work. They can reduce the cost on the order of maybe 10x. Here's another concept that has gained a lot of popularity recently. So the concept here is called weight sharing or parameter sharing. So this one's a little more complicated because what you do in these scenarios is you basically combine the optimization of the controller and the actual task itself. So this image on the left, my left, right? The diagram here shows how you may design what's called, again, the parameter choices or the search space. So you actually have in this case, you're trying to design a neural network architecture or search for it, so NAS, and you have different options for, at this point, I could do maybe max pooling or different convolution operations. And within the convolution operations, maybe there's some different choices about filter sizes, etc. And so you actually construct this really large graph that includes all these multiple pathways. And the controller is trying to optimize its belief over the optimal path to take within the network. And at the same time, the weights of the network are being optimized such that it gives the controller more information about how useful those paths are. So the controller's basically sampling different paths and subpaths and making decisions and getting feedback about how those are performing while the weights are being trained themselves. And so when you do this together, drastic cost reduction. This can be on the order of 1,000x cost reduction. And then the one thing here is that usually what happens is you simultaneously train the controller and the task itself. And then at the end, you can ask the controller, hey, what is the best path? What is the best set of parameters that you believe? And you can either take the top one or maybe some top k, and then you would train those from scratch on your final task. So going forward, we talked about where AutoML could be applied, gave you insight into what AutoML is. So now let's talk about where we headed with AutoML. So in the future, hopefully AutoML will continue to expand to new applications and tasks. It's already made pretty big impacts on things like video, computer vision, text, tabular data, and more. And even within those subfields, the question is, can we push into new areas? And this kind of gets into the concept of, there are lots of fields that have ML experts currently, but how can we, again, lower the barrier to entry for people that want to use machine learning? And areas that have very smart people and scientists looking at things like climate change and deforestation, how can they also get the ML expertise on hand? So hopefully AutoML continues to push into many, many regions. And there's other things that will help that. So again, cost. When the cost goes down for AutoML, that essentially lowers the barrier for machine learning tasks in terms of, right now people definitely need lots of labeled data, lots of compute, and even machine learning experts themselves. And so hopefully AutoML will continue to drive down some of these costs for machine learning. And also more accessible. So I'm here today to talk about some different components of AutoML, maybe educate a few of you on what it is or where it can be applied. And so I hope that the community continues to expand, where people become more familiar with these concepts, and they also show up in machine learning libraries. So it's not just, hey, there's this idea I want to try, but I have to implement it. But how can we actually make AutoML more accessible for new people, and maybe even non-programmers as well? So I hope that these concepts become more available, and you'll see them more in different machine learning libraries. Great. So in conclusion, AutoML can exceed ML experts at many different tasks. It allows non-experts to solve machine learning problems. And in the future, hopefully this continues to drive down the barrier to entry, making it easier for new problems to not require as much data or machine learning expertise. Okay. That's all I have, so thank you so much. I think we have questions, right?
Yeah.
Great.
Take questions.
All right, hand in the back.
6 minutes.
Okay. So the first question was, how do you update the... Yeah. Okay. How do you auto-update the test data set in terms of... Oh, I see. So I think the answer here is, you have this inner loop and this outer loop. And even the inner loop, the feedback that it's giving to the controller should probably be more on like a validation set. So something that kind of acts like a test set, but isn't really your final test set. Otherwise, yeah, you can get into this problem of overfitting to the test data. Does that make sense? Yeah. And then the second question was, how are things available right now for AutoML? There are a few things out there. I wouldn't say anything's readily available in the sense of, you can just kind of use it at hand. In terms of some of the, especially for deep learning, there are some packages maybe that aren't using neural networks that do have some AutoML components. The other thing is that there's a spectrum of, some people won't, AutoML can mean different things to different people, where some people want it to be this black box, I don't need any programming experience, I just throw in my data and I get some classifier, whereas other people want to be more hands-on and kind of try out their own things. So there's a range. I don't really have a good answer as to this is where you should go to get that answer met, but that's kind of the point that hopefully in the future we start seeing more of these libraries available. More questions? Yeah, right here.
So one of the slides mentioned that you use gradient methods. So how would you, I guess, approximate the gradient for something like number of layers?
For something like number of layers, yeah. So the question was, for gradient-based methods, how would you, because sometimes the gradient for some problems or some search spaces are hard to actually collect. So how would you approximate things like number of layers for gradient-based methods? I think the answer in that case is you can have different paths, and sometimes the path is just like an identity, in which case, even though you still have like n layers, if some of those are identity, then it's kind of like having more or less layers. Does that make sense? Okay, so I think your question was how do you figure out like, if you have a gradient in terms of like, how many layers should I have in the network? So the layers one, some of those might have different answers, but the layers one, you could construct a graph that has up to n layers. So that's like the maximum layer size you have. But some of those paths, at some junction, you may choose, I could have this operation or this operation or this operation. And one of those operation types could be identity, which is essentially not having a layer. So you could have a max of n, but depending on the number of identities that are chosen, it's really a smaller set of layers. Back there? Yeah. So I think the question is talking about that inner loop and how do you reduce it? And I think you also brought up the concept of like, is it like single threaded or is this, multi-process? Yeah. Yeah, that's actually a really good point. So there's two things there that I think you brought up. One is if you have this inner loop, oftentimes you don't need to, the controller can output a bunch of workers to try out different things and then get feedback. And in terms of if you want to like do early stopping, yeah, you can create, one method is to sort of create baselines in terms of here's the best result I have so far, maybe the average, and you can look at some new trials that are getting off to like a slow start and kind of stop them that way. Yeah, so the answer is, I think yes, of what you said. Good point, thanks.
Thanks, Adam. Okay, I want to remind you something. Here, we don't have that much time to take all questions, but based on my experience, it's a great opportunity to connect with each other, to have a follow-up questions. Yeah, are you open for connecting with me?
Yeah,
sure.
Feel free to connect. All right.
Thank you.
Thank you.
Thank you, Adam.